What is blockchain mining? What is Bitcoin mining? And let's say that we have a block, and this block is composed of some data, whatever that is, the transactions, the data, the stuff, okay? And I'm just calling it stuff. But we've got a slice, an array of stuff. In my example here, we're going to have two chunks of stuff, whatever it is. But that stuff is a bunch of bytes, okay? So however we lay it out as a structure nicely in the program, we can serialize it down to it's this set of bytes, okay? Now, I'm going to use this same example again here in a bit when we talk about, probably in the next lecture, about Merkle trees, but in this context, we've got these set of bytes, and we have this thing called a nonce. A nonce is an integer value that's going to count up over time, and we're going to start that guy out at 0. So I've got a little tiny 0 in there. I'm probably going to count it up easier where I can write easier than that. But collectively, we've got data, and we've got this nonce that's 4 bytes. And it could be bigger. Could be an 8-byte integer, but in our example, we're just going to use 4 bytes. So we take these pieces and we pass it to our hash. Remember, we did a hash string, but we could have had a hash byte that took different chunks of bytes, and we pass it these 3 sets of things. Out of that hash, we get some value. 0x, because it's hexadecimal, 14C3 something. And we say what we'd really like to have is we'd like to have these out here, these first 3 out here, be zeros. So we want these first 3 to be zeros, and we see that we got 14C. 14C is not zeros, so we're going to go in here and we're going to take this 0 instead, and we're going to make the nonce 1. Now this changed 1 bit in this, but remember, in our system of hashing, we've got the input, and it maps in a relatively random set of values to the output. So there was our first one at 14C. And we've changed it. Now we have this data, but that maps to something completely randomly different down here. We do the same thing. This stuff hasn't changed, but this is now a 1. We serialize it, we hash it, and we get 0x22b1. And the rest of it. And we say, 22b is not zeros. I want zeros at the beginning of this. So what am I going to do? I'm going to loop back around. I'm going to change my 1 to a 2. Now, we haven't moved our data much, but we've moved it over here to a 2. And when we hash it, we get something completely different. We get 0xF312. Okay, it's a value. It's not zeros. And we sit here and we loop, and we keep counting up. 2, 3, 4, 5, 6, 921. I got it. Okay, 921 is the magical value. At 921, suddenly, we serialize this. We hash it, we get 0x0004 something. 921 is our magic value. And if we do this in the blockchain world, Bitcoin world, and you are the first one to get to this magic value, okay, your hardware was fast enough, you were lucky enough, you got there first. Guess what? You get a reward, okay? You are the person that has successfully mined this and found the magic value with the correct bits in it to say, by golly, I won the race. So you announce this to all of your friends, about 11,000, 12,000 of them around the world. I found the magic value. And they go, oh, it's really easy to check the magic value. We just stick the magic value in, we do 1 hash fast, and we go, yeah, you found the magic value. And so they all agree that you are the person that won the race, and you did the mining, and you found the golden magic value. And these magic values are worth a lot of money if you happen to be the person that can find it. Now, this magic value, when it gets created, is the thing that we put in as mining. This is the reward, and this is the process of proof of work. Here is the work. Here's the process, the serialization, the hash, the nonce, the calculation, and what it does with that hash. And the faster you can get to this, the more likely you are to be the person that does it. So by fast, we might say, I saw the block, but instead of having one computer do this, I will take 1,000 computers, and each one of them will be given one result in here, one number to work on, and each one of this 1,000 will then do the hash. Each one is relatively fast, but now we've multiplied by 1,000, and we'll get a result. That's a mining pool. Or you might say, you know what? I will step it up. I will make this hashing process in hardware. So instead of doing, 2 billion hashes a second, I can do 200 billion hashes a second. And I'll take 1,000 machines. And with my 1,000 machines and 200 billion hashes a second, I can get through a lot of hashes. And instead of just sending one number to each one of these, I'll each give them a starting range of 1,000 values. And if none of them find it, we'll rerun it across the network and we'll do the next hundreds of thousands of values in 1 second. And that turns out to be what most mining companies are doing. They have hardware, they're distributing this across many different systems, they're in hardware, they're literally running hundreds of billions of hashes. Now, every one of these hashes takes electricity. I mean, it is in hardware, it's very efficient, but it still takes power to run. And currently what we see is that something like the amount of power that's used in the country of Denmark is being used in Bitcoin doing this process. Every day it's like Denmark. So this means that there's a lot of power. And power is not free. The cheapest places in the world to get electricity is below the Three Gorges Dam in China. So there is an awful lot of mining going on in China. And there's research to show that the value of Bitcoin over time is really an arbitrage between the cost of electricity and the mining process. But this produces a lot of pollution. Now, Three Gorges is hydroelectric, so that's renewable, but lots of other places in the world we see mining going on that is not renewable. In fact, there are a couple mining companies that have moved to Wyoming because we have cheap coal and cheap power here, much cheaper than California, and they do mining not so much on Bitcoin, but on other networks that use proof of work. And the reason they're here is because of cheap electricity. There is cheap electricity in Washington below the Grand Coulee or in the area of the Grand Coulee Dam. Now, sometimes we want to do things where we say we have electricity that is actually of zero value. And I've had a number of discussions with a wind farm operator that they'd like to be able to turn their spare wind when they have no customers and they are not producing power into mining to use it up, because otherwise they either stop the windmills or they, just throw away the electricity. So there's possibilities there of finding a way to do this efficiently and actually use up a resource that isn't being used. But this process and the mining is assignment 2. And basically, what do I give you? I give you a block with a number of transactions. I think they're preset. And you get to implement the thing with the nonce. Basically, this loop wants to loop forever until it meets the criteria, whatever the criteria is. And I have some ones at the beginning that are 0 digits in the hex string. That's not the most intelligent criteria, but it's an example of a mining process. And you basically just sit there and loop until you get the criteria, you exit, and here's the answer. There are test cases for this code, and it reflects well on the capabilities of Go as a programming language, because literally I take the data and I pass it off to something that serializes it and returns slices of bytes. We take the nonce and we use things that are built into the library to convert an integer in a standard fashion to slices of bytes, so that you don't have to worry about whether your hardware is little endian or big endian or some other arrangement of the underlying things. It will consistently return an integer in the same order, in the same fashion, for the same kind of encoding. And then you do the hash. When you get done with the hash, you want to print it out so that you can see if you get 0 digits. Okay? And you take a substring of it and you see if those things are zeros. Now, when I first test this, I do it with a very small thing, like a 1 in 16 chance of getting this. So I just want to look at it for a single 0. Now, the homework assignment asks for 4 digits of zeros at the beginning, which I think is a 1 in 65,000 chance, and some of these things will run for a while, even on a reasonably fast laptop with doing this hash maybe 100,000 times. But that's the picture of this is mining and this is what you're looking for. Now, when we look at this in terms of sets, blocks of data, okay, what we could do with each one of these blocks is we could have a hash for each block. And we've got a whole bunch of these little blocks of data. We could take the hashes and then, well, a hash is basically a set of bytes. So we could hash multiple hashes together since they're bytes and get a new hash. And so if you start out with a bunch of data, and let's say we've got 3 of these things, and then we produce hashes, which are bytes. They're all the same length. But then we take pairs of these and we produce new hashes. Okay? Well, we don't have somebody to pair that with, but we produce a new hash. And then here we have a pair and we produce a new hash. This process is a Merkle tree. We're going to walk through that in some detail next in terms of how we build Merkle trees out of hashes. But I know in other classes that people have taught and done Merkle trees, they had an implementation that was about 1,000 lines of code because they built these things into data structures. In this class, my solution to it is 32 lines. I have seen implementations from students as large as 41. Okay? Because we're taking advantage of the ability to go from structured data into bytes and then just treat everything as bytes and work through it. Now, the implementation I'm showing you has limitations. It doesn't do everything a Merkle tree can do. Okay, and I'm not claiming that. But it works for this application, and it's short, and it's faster than one that takes things as chunks and structures and passes around pointers and builds a tree. And no, we just convert it to bytes, we run down through this thing fast in a loop, and we get an answer. So it's not a huge piece of code, and it reflects well on the Go programming language. Let's take a look at Merkle trees and how we work through the hashes in Merkle trees.